last time we did the beta prime, we derived the posterior distribution. We used the computer to put the distribution all up. So now, sure, we can come up with the prime, but how do we decide the parameters of the prime? What are the things that we need to focus on? So we know what a beta distribution is. What is the density of a beta distribution?
Density, it's 1 over beta, alpha beta, beta to the alpha minus 1 here, and then 1 minus x to the beta minus 1.
And so if you use the parameter, then it'll just be theta. Now, what is the expectation of a beta distribution?
You'll have to remind us.
The expectation of beta is alpha over alpha plus beta. Expectation is nothing but the theoretical mean. Yes. So,
And like, just to remind myself, the way we could derive that ourselves is we would integrate the function at x times the function from
exactly, yes.
negative infinity to positive infinity.
Oh, good question. 0 to 1.
Oh, okay. That's good to know. Thank you.
The support of beta distribution is between 0 and 1, including 0 and it's continuous, doesn't matter. Which is why this is a good candidate to model probability, right?
And it's,
Because probability is between 0 and 1.
it could vary different. It doesn't have to be between 0 and 1 depending on the function, correct? Or will all distribution functions?
No. Beta is between the support of beta
Correct.
is on
You
0
can
1.
scale it.
Like Gaussian, for example, doesn't necessarily.
Negative infinity to infinity.
Oh,
Exponential 0 to
okay,
infinity.
okay.
So the support depends on the random variable. Beta is between 0 and 1.
Do you happen to have a nice chart of all the distributions and
Yes, I do.
Which I would appreciate that very much. If you
Yeah,
could send
I'll
that.
post it. But find it in Google also.
Yeah, I figured, but there's.
There is a book by Casala and Berger. And it's a nice book that I used in graduate school for one of my classes, or made to use that one. So at the back of that textbook, you can find relationship between one distribution and another. And there's this giant diagram where it goes into, okay, the ratio of these two will become that. You take the square root of that, it'll become this. So it's very nice. That's a good book. So if you Google Casala-Berger distribution chart, it'll pop up. So the expectation is mu. Alpha plus beta will determine
This one.
how concentrated. Yep, there's another one too. Let's look for a graph or connection diagram, something like that. So the main expectation is alpha over alpha plus beta, and that is mu. The denominator is going to decide the concentration of the density curve. We will go over that when I simulate. So your book, I believe, uses kappa. It is the concentration parameter, and it pretty much will tell you the number of, flips that you want to make in order to sway your estimate either toward the likelihood or away from the likelihood and toward the prime. So we're simply parameterizing alpha and beta using just one variable, kappa. So alpha over kappa would be mu, which would mean alpha is kappa times mu. The next one is to solve for beta. So alpha over alpha plus beta is equal to mu, which would mean alpha is equal to mu times alpha plus beta. Alpha would equal to mu times alpha plus mu times beta. Move mu times alpha to the other side. Alpha minus mu times alpha would be equal to mu times beta. I can pull alpha out and I get 1 minus mu equals mu beta, right? So if I rewrite alpha, which is kappa times mu, the mu's will get cancelled, and kappa times 1 minus mu equals thing. Yes? In a Bernoulli case, alpha and beta will decide how the failure and success are going to change. Do you agree? Last time, when we changed the value of alpha and beta, the shape of the beta distribution changed in terms of skew. So whether we're going to load on X or on 1 minus X, the failure probability is purely determined by alpha and beta. But if we go back and look at this expression, I'm going to simulate or do whatever analysis in terms of, or from a Bayesian perspective, using kappa, fix some value for kappa, and 1 minus mu. Well, mu is the estimate of the probability, right? So K times failure probability, and K times, or kappa times probability of success, right? So I'm pretty much going to adjust mu so that I get different values for alpha and beta. By all means, as I change the value of kappa, alpha and beta are going to change. So either you're going to move toward a positive skew, negative skew, or right in the middle. Does that make sense? So when would it be same? Want to take a guess? Right, alpha and beta.
For what kappa value?
Kappa is fixed.
Oh, for what mu value? 0.5.
0.5, right?
Yeah.
So when it is 0.5, you get kappa over 2. Well, if that is the case, then when you have 50-50 chance, then the distribution will have no skew. We saw that last time. Not only that, if alpha and beta are one and the same, then it's more uniform-like, or bell-shaped, not bell-shaped, concentrated in the middle rather than skewed on one side or the other. We did simulate last time. So the idea here is to use the value of kappa and mu to determine values of alpha and beta. So all these simulations for different values of kappa and different values of mu after we are done here. That is one way of performing simulations. We always base it on other parameters. So the posterior depends on alpha and beta. Alpha and beta would depend on kappa, right? So we are parameterizing it in such a way Well, if I can simply estimate this value of kappa, estimate a proper value of kappa, I can find alpha and beta given nu, and then go from there to find posterior. So in this case, we are parameterizing alpha and beta using the expectation. Good. The other way to parameterize is to use the mode. The mode of beta okay, that sounds right. So alpha minus 1 divided by alpha plus beta minus 2. So we can use the mode of beta to estimate the values of, mode of a beta distribution to estimate the values of alpha and beta. So alpha plus beta is nothing but kappa, right? We already determined that. So m will be equal to alpha minus 1 over kappa minus 2. M times kappa minus 2 would be equal to alpha minus 1, which would imply alpha would equal to m times kappa minus 2 plus 1. Of course, if we're going to use the mode, kappa better be greater than or equal to 2. So we found alpha and wrote alpha in terms of the mode m. Do the same thing with beta. So m is equal to alpha minus 1 over alpha plus beta minus 2. So m times alpha plus beta minus 2 would equal alpha minus 1. Yes. And on that side, I'm going to rewrite alpha as m times kappa minus 2 plus 1 minus 1. Correct. Replacing alpha by m times kappa minus 2 plus 1. Those two would go away. M times kappa minus 2 would equal to m times alpha plus m times alpha plus beta minus 2 times m would equal that. Have m in common, so I can cancel m. So alpha plus beta minus 2 would be equal to kappa minus 2.
You're all like, I don't see it.
We're going really fast.
I mean, I see a couple looks.
Yeah.
It's like the pluses or minuses, I think.
There we go.
2 minus 1.
Okay, cool, now it all works.
It all works out now. So it has to be plus and kappa has to be greater than 2. Greater than 2. The 2 in the continuous. So that in terms of mode, beta in terms of mode, kappa greater than 2, because if it is equal to 2, we'll have alpha equals 1, beta equals 1, which is the other form. Brilliant.
It also has that kind of not symmetry